Good morning, and thank you so much for the invitation to the CCA. The interest of this presentation is to share with you a little bit about the work we've been carrying out. Several colleagues in the university and the National University of Costa Rica with the application of steady isotopes in the precipitation, and to say that really the talk is oriented originally only in the part of the model, but I thought that maybe it was more convenient for everybody to have previously some countings on the observations we did and why we decided to make a model of the system. So we had a previous experience in the study of transportation of humidity related to precipitation towards Central America as a focus of one of the tropical areas, and for that we were using transportation model, Lagrangian and Flex. Maybe Paulina has shared it with you, but when we proposed to our host to model the domain of Central America, we had a problem, and that is the water masses are so big that the signal is practically a signal from an ocean source, when in fact we know that locally it is not so. So we had the challenge how to work a complex domain, very small somehow, with models when the resolution is limited. And then numerically we could say, well, I increase a lot my resolution, but we all know that models do not work that way. And what we did was to say we will determine what is the maximum domain that we can represent, what is the highest resolution reasonable grid for our domain, and what our most important processes, and we find a solution in the physical tracers steady isotopes for precipitation by rain. I go back to Costa Rica, and then isotopic hydrologist comes back to another university in Costa Rica, and after finding that he was working with shallow water and underground water, and I was working with the transportation, and I needed to validate the model. We needed to integrate the network of isotopes for the tropical ecosystems, because we know there were other colleagues with similar opportunities, okay? So that is the way that we have this network that integrates people from different areas, physicists, chemists, biologists, and some other professionals. So then why? We worked then with the sinks and the sources, and we have more or less the distribution of the main transportation areas, as we can see, except continental regions that are quite wide. The transportation is oceanic, and the question here was, in what way can I prove that in this little part the oceanic source, even if it is the main one, in some parts of the year meteorological data tell us it's not the most important one. So we find a wall of people who tells never. The region is so small, and the same is with the Caribbean, and in such a small part the superficial part is so prevailing. So then we went to show that they were partially mistaken, because the regime of a precipitation of such a small area has very local characteristics related to the part of topography. So we have an idea of the Caribbean coast of Costa Rica to the highest port, that is 3,815 meters in the associated network. So even if we have a huge mass of water coming from the Caribbean, when it crashes with the topography, part of the water that is not allowed in the basin starts interacting with everything that is on the other side. And in the Pacific sector, or in the region of the Pacific, it's where all the superficial processes start being fundamental, so later we can help activate validate the local. And then the first thing is to carry out the test. So we can determine that with the steady isotopes in the Caribbean regime, we have a very enriched value of an oceanic source, high evaporation, and this is the climatological yearly model, and this is the isoscaping that we have. The punctual data measured in particular stations in these points in red and in these points here in blue, and the precipitation regime. And this map is utterly important for us because having values, more impoverished values, indicate this zone is not completely subject to transportation. Here we can understand it as the red zones can reaffirm that the transportations come from a continental source, and when the region comes from green to bluish, the transportation does not count as the main mechanism for generating precipitation locally. And so when having this information, we can say, well, the model somehow knew this. The model tells us where the transportation is prevailing in the Caribbean regime. In the Pacific regime, the transportation is below. It's a very small transportation compared to the Caribbean one, so we become very happy. And what do we do? So what we can represent? Because this is a validation in a climatological scale, and so when we go to the monthly or daily series in a longer period of time, the variation is quite high, and the image we have here gives us a representation of what is happening in a large scale in the region. So we need to go to another scale. And this is the red part, high evaporation, and the corresponding blue part. And then we go to look for more stations distributed along the territory. And we say if we have observed a characteristic of a higher scale, it would be then that the information of the physics proxy can tell us how is the behavior of a rain in a yearly scale. And then together with some regions of Mexico, the same in Central America, we share the period of diminishing of rains, that we call it the little summer. The question is, this information would allow us to determine all the variations going to the right-hand side marked with an asterisk correspond to the Caribbean regime, but we realize that some stations, as we move towards the Pacific, start having a bimodal light bimodal behavior. And then we are going to be checking the location of each one of the stations, and we realize they are not exactly in the Pacific coastline. And then we have to change the monitoring point in order to guarantee that we can observe the signal of the MSD as part of the signal. Currently, the registry is just a few years, so the curves are not as consistent as they are for the ones that have been there monitoring for 10 years. So then, the steady isotopes allow us to make a transition from the climatological scale to a scale of a yearly cycle. And what we have to see is more or less, these are the processes that we want to represent. We want to go to scales as big as we want using the speleothems, but we have a problem, and that is when the samples, in the case of the speleothems, correspond to a solid sample, we have information only on oxygen but not on nitrogen. That would be no problem, but we are mostly interested in the driest regions, and the study requires to understand the eleutherium, and that is aside from what happens in a dry situation, and then we lose that part of the information. But well, let us go to another scale, and we know what happens in an average in 1 year, and it would be that these implementations allows us to understand what happens when we have more extreme events. And then, fortunately, fortunately for the observations, and not very fortunate for the farmers of the Pacific coast in Costa Rica, from 2014 to 2016, we had a very severe Niño affecting the country, and the points of monitoring had been located also in the Pacific. That means then that we have a complete series for the period of the development of a Niño event. And what are we interested in determining here? The isotopic information can tell us something about the conditions of the drought related to El Niño event. So what is the mechanism that we are identifying through that signal? So here we have the peak of the event. And we are interested that the excess of deuterium is falling. In the paleoclimatic registry, it's a pity not to have hydrogen or nitrogen information, because when we see the signal of oxygen 18, we do not see a variation related to the development of the event. It doesn't happen either with hydrogen 2, but when we do the identification of the excess of deuterium, we can see the change according to the conditions that are becoming drier. So the question is here, the excess of deuterium for us starts being a signal that allows us to identify when a dry condition is being developed. And the question is why? Because the excess of deuterium gives us information about the condition of losing the humidity of water in the soil, and important variations in the rates of potential transpiration. What was happening that when we carried out this study a few years ago, it was said, well, the impoverishment is caused by a signal related to more stratiform rain, and that we can see that in the isotopic formation, but later that's why we have it marked here. Is that really true? And that happens that the signal is very similar, but in this case, the excess of deuterium does not correspond necessarily to a signal of a stratiform convection, but the loss of humidity from the soil, and that is the signal we are watching. And then we go to another scale, and that is the scale of the meteorological events or extreme in the scale of atmospheric time. Unfortunately for the research, we had the Hurricane Otto in 2016. It was very important for us in Costa Rica because it is the first hurricane that crosses our national territory in the category of a hurricane. We had no registry of any other before, and it was formed at the end of the year. It was at the end of the season almost, with particular condition and a coupling between a Kelvin wave and a west displacement, a tropical wave. It was the formation in downwards, and it had a blockage on top, and it stayed for a long time, which made it possible for the hurricane to get more energy, and it crosses in this area the border with Nicaragua. And during the development of the hurricane, we receive information that everything is very dangerous. We have not had a hurricane before crossing our country. And my peer, Ricardo, told me I will pick up the data. Let us see what happens. And Ricardo took his car and took rain samples in different points of the national territory. So it is a very valuable set of data because it is unique in its class. And besides, we could have measurements with high frequency with lots of people who contributed collecting samples. The important thing here is summarized in this graph here. The green dots, precipitable water vapor, oxygen, 18 in these little diamonds of a purple color. The important thing is that just when the transition happens to category 3, and that is when we have in the monitoring side the maximum peak of intensity of the hurricane, they trigger the content of the waterfall rain. This indicates the test that what we have a sample in the surface, we are having information on the quick transition and the very quick release of a latent heat just in the moment of the transition. Why is this important for us? Because that allows us to connect the scales and determine then that we can obtain information of a process that is happening upward with the samples that we are collecting in the superficial part with a very high preciseness. And somehow it is to have the opportunity to start implementing microphysics together with the information on the surface. And then up to here, I would expect that you agree with me that isotopes are wonderful. Okay. So what's the importance of this? That then we can make a connection between the time scales that go from processes that happen in the microphysics scale up to what we want to rebuild in time when the traces of the condition allow it. And the objective is that it would be then that of this information we can study better the systems of for rainfall, and we connect this with the modeling. But our region is complex, and the nightmare of the modeling, representation and parametrization is quite improper in many cases in the models, because we insist on keeping using models that were not designed for the tropics. And we have 2 or 3 choices. One is not to model, the other one is to insist in the non-tropical models or to try to tropicalize the models, and each one will be the favorite choice. And many of these we were tropicalizing the models, and the problem that we have with this is if we use the same parameters, we will continue having the same problems. And since we are very stubborn and motivated, the option is good. Why not try to use this physical process in the numerical models and to see in what way we can start generating not better, but to redo or rewrite many of the parametrizations. Why? As we saw before, the observed data allows us not only to connect the scales, but also it is quite consistent from the theoretical point of view, all the part of thermodynamics, with the process that happen in the surface, and that is the ones that are more difficult to represent in our region. Okay, and then why do we select this proxies? Because it gives us information about the mechanisms, excellent proxies on the conditions of saturation, and this is very important in domains where we have changes of temperature and saturation of water vapor. Why? Because this allows us to obtain information on the status of equilibrium between the different stages of water, and that is what we are going to be exchanging when we have the occurrence of the different process in the point of interest. And the question is, knowing that the system is complicated, can we model it? We could accomplish modeling the transportation in a climatological scale, and then we become ambitious. And what are the conditions that we have? A very heterogeneous terrain, coastline, forest, the development of extreme events in the Pacific area of the country while the Caribbean is flooding at the same time. And then the country is small, reasonably small, and that allows us to go to different places and to obtain different points of measurement, and we can carry out automated measurement, and that facilitates our life a lot. And then we decided that, well, yes, we think we can model that system. And then the first thing we do is to make the decision about what model to use. And the isotopic models, we have several. Now Worth even has an isotropic mode that can be used. And after carrying out the review with several peers, we decided to use the spectral regional model, the GSTM, developed with the peers in Japan, and what will be in the intake data if we go in the same model a bad resolution and a low quality intake data, we will get a bad result. And the first review is we are going to be reviewing what data we will be using, and to determine that if the data can reproduce reasonably the characteristics of the system. From the practical point of view, when we use a global model, we already know that the representation in our zone will not be the best, but we want to see not to have the fields of humidity lost. So the first checking we do, we take the hybrid of the ISO GSM, the spectral global model. That is, first we were using the ISO RSM, and we start checking that humidity is where it should be, the intensity of the rainfall is spatially consistent, and we carry out a separation in different boxes, and we are interested in seeing what happens in box number 9. That is the area where we said, okay, if the representation of rainfall vapor is decent, then we will say that the product of the model is also it. And then our zone number 9 is but nevertheless, we are in the 72%, and we could accomplish it, and we are not in the best conditions since we are in India, for example, when we have the best representation with the model, but we can say that it is decent, and that we are aware that one of the reasons why the representation is not the best is the result that we had local conditions that are very singular, that we cannot ask with from a model with grids in the global scale. So then we select a model of the region, and previously we have to know, well, what do we have as observation, because we have to validate the model. So this is the model with which we did the simulation, and this is the distribution of logs we have for Central America. You cannot see it very well, but I tell you, this is meteorological stations in blue, dots for measuring water vapor in red. In yellow, we have the points in which we have isotopic monitoring, and the others are validations also of the column, and that is the distribution. It's maybe not the best from the point of view that one of the particular areas of interest, and that is this region, practically has no observation. So to carry out a validation for the total Central American domain has the inconvenience that it will be biased towards the Pacific sector in the moment you make the decision and simply you evaluate it, when we have absolutely everything we need, and in our case in particular ways our interest, and then we carry out the selection. When we did this first selection, besides, we wanted it to be a little bit difficult because we have a wider coverage of stations, but we wanted to distinguish the points in which the registry for observation was at least 30 years old. The idea is to carry out a long follow, and we saw the registry of Costa Rica. The most uniform one is from 1947, and we selected the regions of that could fulfill with the ideas of the 80s. So we have less points of measurement than the ones present in the region. So what do we do? The next point is what is the resolution that we can reach, and then we have to decide if we use the model in one hydrostatic region or a non-hydrostatic one, and then we commit to a resolution of 10 kilometers. It's not the best resolution, evidently, because our domain is very little. Nevertheless, it is a good resolution, or enough resolution as to identify variations in the distances that we have where we have a meaningful variations. Temporary resolution 3 hours, 12 levels. And then we wanted initially to go to a bigger domain, but we have a computer limitation, evidently, and we decided to shorten the domain. And for us, it was very important to contain in our model this region of Colombia due to the characteristics, particular rainfall conditions that are quite similar to the regime of rainfall of the South Pacific line of Costa Rica. Instead of keeping the domain upwards to the left, we wanted to guarantee we had this part of Colombia and also Panama. So we carried out the simulation with the support of the University of Tokyo, and we were running the model for a long time, for a good time. And then when we started it, we finished the simulations, the Otto hurricane came, and then we could measure for a few years, and we could have the hurricanes Otto and Nate affected us the following year, and then we also wanted to model it. So then the superficial validation, that is what we do at the beginning, and then to verify what do we have. We know that in that scale and with a model that evidently cannot represent all the characteristics, we are interested at least that the basic fields are represented in a reasonable form. And then we do two things. We take the model, we run it in an isotopic mode. We take the model and we turn off the isotopes. Why? Because we are interested in proving that when including the isotopic information, really we have a meaningful gain. So this rainfall, monthly values, and then we get very happy because the area we're most interested in is the Pacific sector, has a very good representation. And the Caribbean area has a representation that is not so good. When we turn off the isotopes, all of these values are below 0.3, so we say we do not have the isotopes, and then the model becomes not so usable, and we guarantee that with the isotopic information the model improves. And the question is, when we have WRF or some other models, this zone is wrongly represented, and this represents better, so what is happening? I got lost. Okay, what we do then, when we want to turn off the isotopes, is that the parametrizations used for the isotopic composition are not used. So we use common parametrizations that we use for other models, the same for cumulus. Please give this man a microphone, and you modify microphysics. And then it happens that when we include the isotopes, the model starts to represent much better all the conditions of the surface coupling that are the ones that define this region. Since this region has the ocean impacts, the isotopic information in the scales of months loses the information of the large scale. So then we have to do the compromise of what we want to represent. When we later generate this data in a daily scale, this improves a lot, but in the scale in the long run, it's information that we have to consider. It's a commitment that we have. And, well, then we can have useful information. What happens here that we have a few observations, we have a very mountain terrain, and we have a bias in the areas with better representation start being those who have, because it's a simplified surface. Temperature, similar conditions, and later the temperature bias was not so big, so we only use a dot point in the Pacific influence area, and we see that in this case the temperatures in the Caribbean have no problem here. We will see the difference with the rainfall. And the most important thing, the isotopic model really can represent the information of the isotopes that were sampled. So we take our log of my friend that is from 2013 to 2016, and we validate it, and we carried out the most unfair validation we can do to a model, that is go point by point. We take the closest point and we use an average of weights and diamonds, and we have the density for oxygen 18 and for hydrogen. That's decent. What were we expecting? because remember, we are asking for a very particular information, very precise, in a very high resolution, because the comparison is made with the new monthly information that is what uses in the GENIT the body of atomic energy, but we are telling the model, I want to know if your daily isotopes are good or not. And the daily scale is satisfactory, and these were the measurement points used for the assessment. And then we say, well, the system certainly has an ability that is reasonable, not only to indicate the meteorology conditions in the surface, but the isotopic value is consistent with what we are measuring in the field. And for us, that was the most important test for the model. It would make no sense to use the huge computer model with the isotopes where the isotopes were wrong at the end. Now we go to the point of interest in the Caribbean sector. The reason why we needed to model it is that the next thing we wanted to know is we wanted to determine if our hypothesis of an excess of eleutherium as a proxy of the beginning of the drought conditions could be modeled. So in order to model it, we have to guarantee that the isotopic information of the domain of interest for studying the drought was reasonable. And this is the region of Nica in Costa Rica, and more or less this is the sector that is affected by conditions of drought that are more severe in all the country. So we are very happy when we say that we are seeing these big dots that are in the domain of interest. And what happens is that the modeling with the excess of eleutherium for the areas of drought is consistent independently if we are in an area of dry forest or in cultivation areas. That's important because the areas, by being so small and having big variations from one side to another in the canopy, the answer to the conditions of drought will be associated with what we have in the soil. And that is fundamental for us to have that well represented, because of the contrary, the gathering that we want to do in the highest part of the atmosphere, getting glowing and getting to the soil, would not be so reasonable. And then what we have, well, the isotopic information is okay. We review the time series for the isotopes as well as for the assessment of the excess of the deuterium are reasonable, and that gives us as a result that the review of the hypothesis of the excess of the deuterium in a scale from the period of 1980 till last year has a ratio of 0.87% with the observation of the meteorological observations of rainfall for these areas of drought. And up to here, I would say that we could be convinced that then the isotopic model represents reasonably this information, but I am cheating because I am only showing a part of the surface. What happens when we go to other places and we check the information of water vapor? Okay, so then what happens? That the 12 vertical levels that we have when we carry out the analysis will depend a lot on the conditions of each one of the days. So the validation that at the beginning was made with the monthly average values had to be discarded because the daily variation is so large in the region that it is not fair for the model to say we do the average of everything and then we see. But when we have the vertical information and we do the separation at the daily scale, I don't have time to bring you the results today, but then we have a much better ratio and we represent rainfall vapor much better, but we have a commitment with the fields of temperature. Now, what happens that the variations of the temperature fields, we cannot say that it's because we have ascending isotopes. When we compare the isotopic and the non-isotopic part, these are practically the same, and that tells us that something happens with the input data that are the ones that we have in the temperature fields. Well, and then what can we conclude? That we are all fans of the isotopes. Well, what is the most important thing for us? That we could accomplish the evolution from the study of the sink-source relation as to studies that can be as locatable as we want. Because when we use Lagrange or Lagrangian or semi-Lagrangian models to study this relation between the sink and the source, we find that the representation of recycling humidity of a local transpiration is not represented by the Lagrangian model. And that is the information that we can have. And we cannot go and accept totally the results that the Lagrangian model gives to us, because it was not designed for that purpose and it does not have that capacity. The advantage that we can have by linking it to the isotopic model, and we become totally independent from the scale, because we can work in a spectrum of temporary scales that is much wider. Well, and then when things start working, you become less ambitious, and I don't know if that's good or bad. But we realize also that the local information of the excess of deuterium connected with the subsurface information gives us the content of humidity in the soil and the variations that exist. And we say, well, if we have a coupled system and our worst representation in any model we use is just the part in which we have the couple of the atmosphere and the surface, why don't we try if the isotopic proxy could also help us a little bit with that? And so this is more or less what we have started doing now in what we call the continuum soil, plant, and land and atmosphere. We know the conditions of under soil, the soil, and on top of that, what can we do? We can do a partition of the fluids that we have, directly calculate and measure the evapotranspiration in a surface. And as of that, we can say, for example, how reasonable are the estimations of the potential evapotranspiration in potential products that are around there, many of them for agricultural applications. Why is that important for us? Because when you increase in our Pacific regime the potential of evapotranspiration indexes, we increase our own potential to have a rainfall by local phenomena, and all of those data the models cannot represent. And so to have this coupling allows us to say, well, we should carry out this modification to the parametrization. I don't know in the case of soil, but the satellite images for Central America are quite poor. So when we use that information in the models, all the rest do not have so many problems. So we take our eyes to the soil and we say we only have to measure. That's the only thing we can do. And to have this information then that is modeled and reasonable, because when we check our products of the model, the soil humidity with the isotopic component, then the result improves meaningfully. Well, what can we do then by having different scales? As we saw in the Otto hurricane, we can have information not only of what is happening in the surface, but what is happening on the top, and that widens from the meteorological point of view, the perspective in which we interpret the results of the model, and also how we represent and understand different processes that are happening, because now it is very fancy, this discussion on how it goes from the stratiform part of the rainfall, and then again it is a choice for having information with which we can make a contrast with the information we have of the micro radars of rainfall or distometers. And the tool is quite powerful. It used to be very expensive. It has become a little bit more democratized, the analysis of the isotopic composition. It's not super economic, but the sampling is simple and the processing of samples is simple also. And there are ways to facilitate the analysis of the samples, and that has allowed us that increasingly the networks of information can start being a little bit more continues at the beginning in the 60s when the GNet started. The measurements that we had were of very punctual events or cases, and now some countries have a permanent monitoring networks, and that's super valuable because that gives us much more information than the one we had with the stations of temperatures of stations that measure temperature and rainfall. And what I like the most of this part is that we are respectful that the tropical regions are totally different, and that maybe trying to make that the tropic fits in tropical things is not the best way, and we can prove it and to have choices for managing it and to work directly from a perspective of modeling that starts being tropical. Okay, it was born being tropical, and that allows it to keep its characteristics and not to have this bias that we started representing the process in a different way when in fact we are not representing them. And for us it is important, but as I was telling you, the region is quite complex, and to have huge masses of water at both sides makes things even more complex. And what are we doing now to generate information in the climatological scale nationally? And this is the focus of the Guanacaste province in the drought. It was affected. Generating products of visualization so people can use them in different variables. We are particularly interested in working with the agricultural, in the agricultural sector, in the evapotranspiration topic, and justly because this is an area where where we have the most impact is the Pix-Cleve basin, and that is the agricultural exploitation is intense. It's an area where there is also salt infiltration. There are many wells. It's a complicated zone in that sense, and the idea is that information also has a social projection and can be used for managing and planning. Well, I was telling you now we are interested in knowing what can we see beyond this, and we work in a new project, and we are trying to determine what is the relation we have between the signal of the isotopic signal of the sample of rainfall with the optical characteristics of rain drops. The next stage will have not only to have the information on the isotope rainfall in the surface in the liquid sample, but also to have the continuum in the sample of a vapor directly injected, and the partition of flows. And again, the problem of the evapotranspiration that is also measured. We're interested with the measurement with authentic heat and sensitive heat, and the most correct way to do is to directly measure it, and with this we have implemented 3 monitoring system with a system of co-alliance of a flow to carry out directly the partition. And this is more or less what I wanted to share with you. And here we have some of the works that we have developed. Some of us some of these are already published and some are in progress. And you can look into them if you want to know specific details about what we have been developed. And our people team is quite big. I represent a very big group of people with whom I work. It is also very good that we remember that we are not only a group, a university, but we are a consortium of different institutions. Thank you so much. The video. I wanted to show your video. When we were with the hurricane, we said, is it that then we have the capability to look at the formation of cyclonic systems? What we have deployed is a simulation of oxygen, 18 and 854 hectopascals, 850 hectopascals. the loss of the mass in the water, and then the configuration that we start having in the displacement of the cyclonic system. That's why I was talking to you about the versatility of the system. This case is the Emilia hurricane. In 2004, if I'm not mistaken, we started generating the historic of all the cyclones that occurred in the modeling time from 80 to 2018 in the domain of 3, and the idea is to verify if effectively the condition of the formation of the cyclonic system respond to the satellite observations that we have. Why? What happens is that when we start forming the cyclonic system, what we have there is an impressive amount of flows and transitions of flows of latent heat mainly. Why is this information so useful? Because justly the variation of latent heat or the release of latent heat is what the water vapor captures in the isotope. The isotope is a kind of a memory of what happens with the air masses, and even if it changes the shape and goes to rainfall in the surface, it keeps the characteristic of having gone through a process in which the release of latent heat modified the chemical composition. And that is the tool that makes it so powerful to capture that information and independently from the processes happening later to be able to have that information in the form of rainfall. So, well, the video is quite nice. And it gives us a very good example of how the formation of the cyclonic system in reality is when we will have the most impoverished values. All the latent heat is released and the water mass loses. It becomes lighter increasingly. Thank you so much, Anna. If you want to use menti.com for your question, the code is 542046. If somebody has any question. Yes. I remind you, please do not tap on the microphone. Thank you so much for your talk. Two questions. When you were showing this spectral global model, you compared it with data of the TRM, and you said that more or less you did it correctly. But if you compare with the zone of the dome of Costa Rica, the model overestimates rainfall too much. And how do you reflect that part in the calculations that you carry out? Because when you validate it, you show circles of correlation. But here my question is, did you notice very well what are the patterns of rainfall? The assessment is done in two ways all the time, and here we only show the ones that we do with the seasons is the one that is more solid. But first we look at the patterns, and the patterns are checked with compounds. What we have done is to use and to verify that the conditions of rainfall, and there is a correspondence because the typing that they are doing with the model data and with the information that we have from the synoptical observations, and we also have an overestimation. What happens is that even if the satellite results overestimates, the model also overestimates. And then the two things come together, but the overestimation reduces meaningfully when we do the change and we use the isotopic information. And in regard to that, it was not clear to me. You said that you use different parametrizations, but how did you do it? In a normal model, let's say, you mentioned WRF. As you say, we really would have to do it more tropicalized or to adjust it to the zone. It presents a serious problem, and by using this isotopic information, it is corrected. My question is, how does that happen? Because it's not clear to me. If you could please be more detailed. Well, what we do is that we include in the equations of the system, we include the thermodynamic one of a saturation of water vapor. So it is not assumed, as many models do, that water vapor has a pressure of saturation that is more or less constant. But what they do is to include the change or the dependency that vapor saturation has on the process of evaporation, condensation, and precipitation. So basically it is these are three additional thermodynamic equations included in the systems of equation, and that allows us to have better numbers. But it has the inconvenience that, for example, if we compare the variation of the parametrization with ISO RSM and we compare it to other models, the additional information or equations that could be included is not the same. It will change according to each model. Each model is conceived in a different way. In the specific case of the call of ISO RSM that has shares things such as the MM5. Hello, it's excellent images. It's not clear how many dots of isotopy of rainfall you have in Costa Rica, because it is less costly than now. But in Mexico, I have a research who is sampling and monitoring, and I think we have one in Veracruz and another in the north, and some peers have carried out campaigns, and these are limited in time. Since the year 2013, the network of the National University that is coordinated by my peer Ricardo Sanchez, they have 10 fixed points for monitoring. Since last year, we added to the network. There we have some points that are monthly, not all of them are daily. Daily, or the most important ones, the ones that are more far away, are monthly. It depends a lot also on the scale of the information that you want to obtain. So that is also part of the decision if monitoring is daily or monthly. And this year we included 4 daily points now. With the campaign of OTREC, we included 12 additional points for daily measuring, and we have another one of high frequency that, depending on the day and the event being developed. The monitoring is done with a variation of frequencies that go from hours, segments of each 5 minutes. So it's 14 points in such a small place. And have the financing ensured to do that for a long term? Well, the budget is to guarantee the sustainability of the most important points, those in flood areas. The ones that are guaranteed are in the drought area, but 2 times a year we want to guarantee it for the next year in 2 parts. We have had the challenge when we decided to carry out the change and to include high frequency, because to collect samples every 5 minutes is very easy. The thing is that the team has, the equipment has a maximum number, I think it's 71 points can be run for 1 day, and consumables, and that is what is costly, but we always try to procure, to have it, and we are working with the points of high frequency, and we were interested in having 2 additional points in the scale of 5 minutes, but that was financially non-feasible, so we worked with only 1. And what happens is that you not only measure 5 minutes, you measure 5 minutes when you have an event that is interesting to analyze. I have a comment about El Niño event. The index was very high. I don't know if you have looked at the propagation, and the signal was not of the El Niño moment. Since you only have that event, I think it was a heating in the center of the Pacific. People from Spain and Italy are saying so. In Mexico, the signal was not the characteristic of the previous Niño. That was temperature. In the case of Costa Rica, the peculiarity was that in spite that the event was not from the point of view of the index as Niño as the others, the signal of drought was as strong as the Niño of 97. So that was the particular interest in that event. So in spite, there were other events in the middle, another drought in 82, but we had not had an event causing events such as the Niño in 97. This surpassed in time Niño of 97. even if the drought, the reduction of rainfall was not as big as expected. That's what I meant. The duration period was much longer. So the country, even now, this year, we are recovering in our agricultural sector from that event, from the point of view of the impact, even if it's not a Niño with a name and family name. The coupling with the oscillations of Caribbean allowed it to keep the characteristics of a severe Niño. Anna, thank you so much for your presentation. And I was thinking, I think it is very important what you are doing to tropicalize it. The model here also. We are very much interested in that. And one of the things that I wanted to ask you, the aspect of the formation of ice crystals in the new model, because one of the things that we have been doing with the Scadinho in the group, carrying out measurements in Mérida, is to evaluate the glacier nuclei. Is there a possibility maybe to include some nuclei parametrization using those values? So maybe we can talk about that later. Thank you, Graciela. That's very interesting. What we have proposed in the level of the laboratory, and honestly, at the moment we are in the process of seeing who funds the idea, is to make the ice crystals grow in a vacuum chamber and to oblige them to change the phase under controlled conditions. So what we do, you inject the water vapor in the online analyzer, and you can get this equation of the variation, so you can obtain characteristic values, because then the growth of the crystals varies depending on the saturation and many other factors. But it would be very useful to generate tables, at least to have an idea of the characteristic formation, and that can be done in the lab scale in a relatively simple way. We have been doing that, is sampling in the field, and there is an incidence, an important incidence of bioaerosol and also the Sahara dust, and we have samples taken, and then we can go to Luis in the laboratorium makes the crystals grow by immersion freezing from that point of view, and basically we have the seeds that you are talking about. And we see the evidence of the sea sources and also continental sources in the Yucatan Peninsula, which is a small peninsula as well in size as a continental area. And we see components that are biogenic. Those are emissions coming from the vegetation. And you said that evapotranspiration is also important, and that will be possibly linked to the nuclei of glaciation. And what we have seen with the observation analysis is what seems to be the key parameter is the variation in the saturation of the water vapor. So if we have the capability of being able to measure it and to determine what is the signal it has, then we could infer, for example, rates of evapotranspiration, condensation, evaporation or variation in freezing conditions, but to have the precision to measure the saturation of water vapor. In the field experiment, that becomes very complicated, doing that in a lab. It is, the lab gives you the advantage of being able to control the things, but then you can create tables in order to use them later. Hello, I have a question. You mentioned that the rainfall depends on the amount of the excess of the deuterium. So could you establish a relation between the mass of the deuterium and the formation of clouds, for example, depending on the concentration of the deuterium, and that would last as the rain, or what? No, to explain it a little bit clearer, the relation with the excess of the deuterium is what allows us to determine the conditions, or the relation of dry conditions. Variations in the excess of the deuterium correspond with the deficit of rainfall. Now, the excess of the deuterium is part of the signal of a potential evapotranspiration. With that, you can determine how much mass of water you have in the surface that is being lost to evaporation. For the other that you were mentioning, the most important signal is oxygen 18, and what is the relation there is between the rate of change, that would be the deuterium, but with the release of latent heat in the air mass. And it is much more complicated to measure because the conditions of the surface are always more manageable for us to measure that in the atmosphere. I cannot think of how to do it. Does he have a microphone? Why don't you use quantum mechanics to model those type of particles? Because it is assumed that classically particles cannot be well studied with electromagnetism. It's not so good, but with quantum mechanics you can establish a relation between the mass and, for example, the power of energy. There is a group in Germany that has worked. The project is called, well, it was an experiment called music. In music, what they did was to use estimation based on the mismatch of the signal, and they carried out an estimation of the columns. Two solids use interferometry to measure the value as such, and not even in the rainfall, but in the water, in the air column. What happens when you compare it with a very few in situ measurements in the column, the result is not so good. But several groups have been. Frankenberg used it with the estimations that are being carried out with different satellites, and this group of music that tried to do it in a different way. It has reasonable results, but when you compare it with GO to measure the composition of air, the result is not so good. Do you have questions, online questions? No. Hello, thank you, very nice presentation. Maybe due to my lack of knowledge, but when you talk about tropicalizing, you're thinking of having real measurements as input in the model, or to change the equations? Where it would be to change the equations. Another of the problems that we have with the modeling is that we have a few observations. If we assimilate the observations that we have, then the validation is not independent. So with the tropicalizing, we refer to have parametrizations that correspond to the tropical processes and not to the corrections at the end, to include the corresponding part to the most tropical parts. Hello, good afternoon. Thank you for your presentation. I have a technical question in relation to the model. I don't know the ISO RSM. I have not worked with it. In spite that we want to separate the signal that the ocean component could have on rainfall, the field of the surface of the temperature of the surface of the sea. How is it considered? It's prescribed. In this case, and this modeling, we used a slab ocean. We didn't do the coupling with the ocean variation. And that, because that's a huge work. Oh, yes, of course, I understand that. But, well, it is prescribed as of a reanalysis, yes, by reanalysis. And that's interesting because to be able to assimilate the variation implies that those fields will be changing because the evaporation on the ocean also changes. But in the part of ocean coupling with the isotopic model, that's something we have not done. That is considered for the long term because our group is relatively small. But then, at the beginning, when you were showing the part of the side of the Caribbean in red and the Pacific area in blue, and you said that these are few elements for humidity transportation, and that is something that you obtained by an atmospheric model forced on the surface. Well, the graph of transportation I showed, there were two maps. So the one on these sides that were the baron, the transports, and that is estimated with the Lagrangian model. And the other is the map of the isotopic construction in the surface, where we have is that the signal of all the parts that you see in red in the Caribbean corresponds to the most meaningful transportation that comes from the oceanic mass of the Caribbean. Yes, but in order to estimate the transportation, you need the data of humidity. Well, these are reanalysis of interim assimilated in the Lagrangian model. Okay, then. So we have a question that came through this link. How can you monitor a drought with evapotranspiration? Okay, well, in an ideal system, you could have your area of monitoring and you have a system. Hopefully, all the humidity sensors you have at different levels, rainfall, meteorology of the surface, and with that you can estimate evapotranspiration. It's utterly important in that case to have the information of the 4 parameters of radiation, and that is the parameter that gives you more problems. The sensors of radiation are a little bit expensive. If you have a meteorological station, the sensors of humidity, you can guarantee that you are calculating perfectly the meta radiation, then you can see what was the transpiration. And that is done with the covariance of a flow to have information of net variation, wind in 3 dimensions. In that case, with the 3 dimensions, winds and concentration of water vapor, you can estimate the flux. And you have the wind in 3 dimensions because you use a sonic gauge. You can know how much vapor goes upward and how much goes downward. And you can relate your measurement of the estimation of the evapotranspiration as of a meteorological information with the net change between the vapor that comes in and the vapor that goes out. If there are no more questions, we thank again Dr. Anna.